Hi everyone. In this video we're going to be talking about applying Le Chatelier's principle in the Haber process. Looking at some of the aspects to Le Chatelier's principle that allow us to predict what's going to happen in the Haber process when we change certain variables. Because just to remind you that Le Chatelier's principle says that an equilibrium system will shift to adjust to partially counteract a disturbance or a change that happens. Okay, so what we're going to do in this, as we're working on this page of the booklet, we're going to identify the different changes that may occur and then think about with that particular chemical reaction, which direction is it going to shift, and then actually identifying a reason for that shift. Okay, so it might be helpful to reflect back on your notes about the way that different properties will, that using Le Chatelier's principle to predict what happens when we change certain properties, so that you've got something close. Easy to refer to. Okay, so let's get into it. Okay, so we're going to focus on using this particular table. Okay, now before we start getting too far underway, I'm going to make a small adjustment into the rows here when we're thinking about concentration, because concentration, as you may remember from when we're talking about it, we can change the concentration of any substance in our equilibrium. So we need to, and that will affect which way it will shift. So we need to be a bit more specific to start with. So you can make these little annotations on your booklet as you watch. Okay, so I'm going to talk about increasing the concentrations of nitrogen and hydrogen gases and decreasing the concentration of ammonia. Okay, because they're ones that we're actually going to be changing in industry in order to produce more ammonia. Okay, so when we're thinking about concentration, so we're thinking, all right, so what's going to happen if we increase the levels of nitrogen and hydrogen gas? Okay, so thinking about our equation, it's going to shift to the right. Okay, because so that it's going to, so the equilibrium. Now, having written the word equilibrium, I'm just going to copy that so that I can paste it the next time I need to use it. Equilibrium will shift to remove the added N2 and H2. So therefore it shifts to the right. Okay, so that's what we see. Now, if we then look at, say, okay, well, rather than increasing the reactants, what happens if we decrease the products? Now, in industry, this happens by actually taking the ammonia gas and cooling it down enough so that it becomes a liquid, and so that it actually condenses out of the system. What we see in that situation is the same shift, that it shifts to the right. So that is, the equilibrium will shift to replace the removed NH3. Therefore, it shifts to the right-hand side. Let's see. Yeah, you get the idea. Okay, now let's look at what happens when we're changing the pressure or the volume. Okay, now what I'm going to do is we'll frame this in terms of the pressure. Okay, just to help try and keep things clear. Okay, so we're thinking, all right, increase pressure, decrease pressure. Okay, so if we increase the pressure, we're going to end up shifting to the right-hand side. Okay, because if you remember the equation that we have 1 nitrogen and 3 hydrogen gas molecules becoming 2 ammonia molecules. So we've got 4 molecules on the left, 2 molecules on the right. And so what's going to happen, if we increase the pressure, we'll shift, and the equilibrium will shift to the right-hand side to favour the side with fewer molecules, which will reduce the pressure. Okay, so if we favour the side with fewer molecules, we're going to reduce the pressure, which means that if we consider the opposite situation, if we decrease the pressure, it's going to shift to the left. Okay, because what's going to happen here, I can just change this, it will shift to the left-hand side to favour the side with more molecules, which would be raising the pressure. Okay, so it would help to actually to provide more gas particles into the system by shifting back to the left, so which is going to then decrease the yield of ammonia. Okay, now let's have lastly, let's have a look at temperature changes. Okay, so, or the second last thing, sorry, we're going to talk about catalyst next. Okay, so if we increase the temperature, then what's going to happen is we're going to get a shift to the left because the forward reaction is exothermic. So reverse reaction will be favored as a way to reduce the temperature. Okay, so that means that yield decreases. Okay, because we are shifting back towards the left, we're getting less ammonia forming in this situation. Okay, so our yield goes down. Okay, whereas if we decrease the temperature, then what happens is we're going to get the opposite. We're going to get a shift to the right. We're favoring the exothermic forward reaction as a way to increase the temperature. Or another way you can think about it would be to replace lost thermal energy. You know, because it can be quite helpful in the situation to think about energy as a term that's included in our chemical equation. Okay, so if we consider it as something that's been taken out, it's going to shift to the side that will replace it. Okay, so it will favour the exothermic forward reaction. So I might just neaten this up a little bit. Favouring the reverse reaction as a way to reduce the temperature. Remove added thermal energy. Yield. Apparently I can spell. Okay, so yield decreases. Whereas so you can see if we decrease the temperature, the yield's going to increase. Okay, the last thing that we're going to look at changing about the system is we're thinking about the catalyst. Okay, so that just like when we've talked about before, when we add a catalyst, it lowers the activation energy. It increases the rate of both forward, reverse reactions. Okay, so it means, so what this means is that we don't get more yield. So we're not actually, it's not helping us to get more ammonia overall, but it means that a lower temperature can be used because less energy is required to start reaction process. Because normally you need the higher energy in order to actually get the reaction to be occurring, to get the particles moving fast enough that the collisions work. But when you can use a catalyst, because you have an easier reaction pathway, so less energy less energy is needed, therefore lower temperatures are required. So that means that because what we'll talk about is that temperature is the one that is particularly tricky because the reaction happens much faster at high temperatures because the particles themselves are moving much faster. You're getting more successful collisions. But we can see from the Le Chatelier's principle just up here that if we increase it, we actually favour the left-hand side, so our yield decreases. So it's a tricky conundrum here that you want it to be fast enough, but you also want to get enough to make it worth it. Whereas, say, if you wanted to boost the equilibrium by dropping the temperature, the rate decreases so to the point at which it's not even worth doing anymore because it's so slow. You know, because in the industry you've got time constraints and cost constraints. You know, you've got plants to run and people to employ and so on. And so you need it to be economically viable, not just chemically viable. So what we will see, we'll discuss a little bit more about the compromise conditions in a future video. But so what we see is the effect on pressure, on the reaction rate and yield, is that as the pressure increases, that we get a greater yield because we're using the equilibrium to shift it across. So we get a greater yield and we also get a faster reaction rate. So we get greater yield due to Le Chatelier's principle. Apparently I can't spell yield, but I can spell Le Chatelier. So there you go. Due to Le Chatelier's principle and greater rate, because you get more collisions between particles. But the thing is that increased pressure equals lots of these bad boys. It's very costly and very dangerous. It's very costly and very dangerous to maintain high pressure equipment. Okay, the potential for things to go bad explosively at high pressure is significant. And so there's safety concerns, occupational health and safety concerns, and all of that by maintaining that increased pressure environment. So it's dangerous and it's costly, but from a chemical engineering point of view, it works. Okay, thanks very much for watching now. Bye for now.